So this in-person, this in-class exercise will be turned in at the end of the lecture today. Okay, you finish everything and turn it in today. So here's the website again. Should I try it? How to change the resolution here? Please just log into my website or just get into my website so you can follow all these steps. If you click embedded devices on the top, and you can see these are the schedules for the lectures. Basically, they are tutorials. So I will give a lecture for each tutorial every time we meet here and explain what's really going on. And you guys just follow and finish all the tasks. So for the labs, these are the schedule for the labs. And adding 2 labs to the semester compared to the past semesters because I think these are super important. I'm going to explain why these are exciting and important. All right. So this for today's lab, if you click the first link, can you all find this webpage? This is tiny. I'm sorry. IT is going to fix this hopefully at noon. Can I get into this page? The first lab? Okay. So the order of kind of the work for today is, even though the lab is in the afternoon, but you can see the lab has all the details about how to install Vim, which is just a text editor. It's not a compiler, just text editor. Why do we have to know Vim? It's because all the Linux interface will be a VI interface. So in the future, when you are working with within a team, doing any of the scripts, writing in the with the server, you just have to add it in VI. So it's basically a Linux editor, and all the commands, you just have to be familiar with it. So be ready on the first day of the job. For this lab, since we are encouraging everyone to install Vivado on your own personal laptop, or you are using the desktop over here, we are not installing Vivado into a server. So which means you are not actually logging to the server to open Vivado over there. You are not really using VI editor for the server, okay? But it's a good learning experience because in the future when you are doing Verilog programming with digital design, it's always Linux. It's always VI. Okay? So there will be a quiz on VI commands next week, which is Tuesday. Okay, the Tuesday during the next week's lab. I'm going to sit with every one of you and give you probably 10 questions, ask you how do you move the cursor down, how do you do the copy and paste, and how do you move the cursor to the top of the page and bottom of the page, things like that. How many of you have used the VI in the past? You? Any of you? Just one? Okay. All right, so install Vim and Vivado. So this first week, just be ready. You can see it's 2017, which is okay. I recommend 2018. But I don't recommend anything newer than 2020. It's gonna be super slow on your personal laptop. It's huge, like 40 gigabytes, Vivado. But even for the 2018 one, I think it's something gigabytes. It's huge. Okay, so use anything older than 2018. It could be 2017, 2018, point 1, 2, 3, doesn't matter. But I think in this tutorial, if you scroll to the top, do I have it here? I must have it somewhere else for installation. Oh, here. So Vivado installation. It's still Lab 1's webpage. Okay? Scroll down to section 2. It's Vivado installation 2018.3. Follow these steps to get Vivado installed onto your personal laptop. Highly recommended. So the lab is in 760, and there's only how many benches? 10-ish, I think. You have been there for Circuit 1 labs, right? 8 or 10, but we have 14 students in this class. So you just have to have your personal laptop installed, Vivado in there, Vivado and Vim in there to do all the design by yourself. There are only like 10 desktops in the lab. It's not a teamwork, keep in mind. This class is not a teamwork, okay? Yeah, it's very clear. Follow these steps. Have your first AND gate compiled onto the IPGA chip and simulate it. Run the simulation, see the AND logic. Okay, lab 1. Very simple. Vivado basics will be today's lecture, and I'm gonna answer, I think, pretty much every single question on the quiz. So when you are looking at the quiz, just keep all these questions in your mind. So first, what is that? What is an FPGA? So it is a chip, integrated circuit chip. It's from Xilinx. There are two major FPGA companies. Put a marker here. Xilinx and Ultra. And I think Xilinx was acquired by AMD. So when you are downloading Vivado, it's leading you to the AMD's webpage. Ultra was acquired by Intel, I believe. So these are the two major players of making FPGAs. So FPGAs are not like all these microcontrollers that you have used in the past. So if you compare FPGAs and microcontroller, you can tell the difference from the internal design, but not the outside, because sometimes you can use the same package. So this is an Arduino chip. It's a 28 pin package. It's a DIP version. Is that 28? 14 on each side. So it's a 28 pin DIP, right? It's a DIP because all these are through-hole package. And for the FPGA chip over here, it has its own package name. I couldn't remember it, but it's definitely a surface mount. You are not starting from the back, right? There's nothing to be started on the back. It's the FPGA chip. And internally, if you look at the diagram over here, here's the microcontroller. You can open up this figure on your desktop as well. You can see for the Arduino's microcontroller, you can see it has a CPU, has all the ports, flash, stores all the instructions, EEPROM, ADCs, ports, GPLs, all these kind of peripherals. Okay, it has analog components, has digital components, but the thing is, when you are using like ADCs, it prevents you from using very small design or small technologies. What does that mean? Small technologies. When we are talking about technologies in semiconductor industry, it usually means the foundry. The foundries could be, you probably have heard about that in the news, right? Like TSMC is a foundry, Global Foundry, or Samsung also have their foundry. So these are called pure play foundries because they don't do any digital design. Nobody in these companies, sometimes Samsung, they have, or different sectors are doing digital design as well, definitely, since they have their digital chips or memory chips. But for example, TSMC doesn't have digital design sectors. It's basically just a foundry. Okay, doing fabrications. It's a Taiwan semiconductor manufacturer company. It's a leader in the industry right now. It's the only company making good yield for 5nm technologies, making all the CPUs for Snapdragon and what's that the Apple, the iPhone chips, like what right now, like A10, I don't know, but all these CPUs, okay, so they require very small technologies because the smaller the chips are, the smaller the transistors are, the higher speed you can reach. Why is that? If you look at the transistor like this, it's an NMOS transistor. If you haven't taken analog yet, which is fine, since we are going to cover a lot in the digital VLSI class. Some of you are not in that class, but which is fine. Have you taken analog?
Yeah, I've taken
Yeah, cool. You are or you have?
I have.
Good. Okay, who else? You have. Okay, cool. But for the rest of you are in my digital class, right? Which is good. You are not. Have you taken analog? No. Okay. So an NMOS transistor is just a transistor running current from drain to source. Here's the gate. The technology means the length of the channel. Here's the transistor, right? So here, this dimension is the length. The length. So whenever it running current back and forth in the channel, the charges up and discharges the parasitic capacitance over here. Okay, you have a longer length, it takes longer time to respond to the clock at the gate. I mean, we just need to know this very briefly for now. So just, you need to know that the technology, whenever you are doing an interview or attending conferences, when people are talking about technology, it's not just the technology in general. It's the technology being used for the manufacturing a certain dimension of the chip. And that dimension means length. Keep in mind, when people are talking about 5 nanometer technology, remember? 5 nanometer is one of the newest we're already commercialized. Okay, the 5 nanometer is the length of the CMOS. Okay, it's really tiny. Okay, but for this guy, because it has analog components in there as well, which prevents you from reducing the size to 5. So sometimes if you have a general purpose CPU like this, which is the microcontroller, since you want to use it for like driving a motor, doing PWMs, or doing analog to digital converter, have all the AO pins receiving some analog signal and digitize it. So you just want to do too many things. It's general purpose CPU. And usually you cannot make it using one of the smallest technologies. So like this one, I think this one was in like 350 or something technology, which is like 25 years old technology. Can you imagine? 350 nanometer versus 5. It's a huge difference. So this is a super old technology. But doing FPGAs, a lot of times you don't need so many analog components in there. You just want to make a digital chip. So most of the cases you can make you can use the modern technologies to fabricate all these FPGA chips. So I think this one is somewhere around 22 nanometer. So you can run this faster, way faster. I mean, the crystal clock for this CPU is around 16 megahertz for like Arduino. It's at Mega 328, okay, which is the Arduino chip. And the FPGA chip we are using, the board is called Basys 3, which is Arctic's 7 chip. So it's about 350 nanometers, and this is about 22 nanometers. Okay. And if you look at the internal structure, and they're very different as well. So for this one, it has the CPU already fabricated inside the chip, as all the peripherals. You cannot change it. So when you're programming a microcontroller, what's really happening is you write the C language, and the compiler compile it into the machine code, like 1 and 0s, and it's being stored in the flash. And so the instruction pointer will take out every single instruction and use them as the input for the CPUs and do the calculations. That's how the CPU works. for microcontrollers, right? But for IPGAs, they're just totally different animal. If you look at the structure, most of the time, for example, for our Basys 3 IPGA board, not for all the IPGAs, just for this IPGA, it doesn't have a CPU in it. You are wondering how does it do all these computations? No CPU? Seriously? How do we run anything on it? It has all these logic gates array. You know, what is IPGA is one of the questions. It's a field programmable gate array. So it has all these logic gates. It's just repeating all these logic units. So what are in there? It's very simple. Lookup table, LUT. LUT means lookup table. Lookup table. So what does lookup table mean? It's actually just cheating, right? You don't have any logic in there. You just tell the lookup table, these are the inputs. If I see these inputs, I need this type of output. It's cheating. Okay? It's basically cheating. So you have all these lookup tables with a flip-flop, just controlled by clocks and some mux, you know. So all these cores, all these circuits are IP controlled. You know, if you ask me to design IPGA block, I probably need like another few weeks to look into the circuits from the papers. You know, I have never designed the IPGA block. But what we know is the fundamental concept is basically just all these repeating logic blocks with the LUT in there. So what are LUTs? It's static RAM cells stores the outputs. Keep in mind, SRAM in LUTs, lookup table, stores what? Stores outputs. Whenever it receives an input, it directly outputs these data values. It doesn't like all these logic gates. You design it to output these certain values. No, it's just, it tells the block, these are the numbers to output. It's already defined in there, like 1 and 0 is already stored in there. That's why I'm calling it's cheating. Okay. So when you program it, we'll program it using Verilog. It stores all these values to SRAM, the static RAM memories. So RAM means random access memories. So static random access memories. If you're in digital VLSI, later in the semester we'll design a little RAM in the simulation and run all these SRAM logic. But now we just need to know that SRAM and memory cells can store a logic 1 or logic 0. Okay, just one logic unit or bit. Okay, you tells it, you get a certain input, it's gonna output the value stored in the SRAM to the output. Okay, it's a table. It's already put in there. Okay, so it changes every time you program. It changes. It's not a certain logic like AND gate, OR gate. It's built-in logic in there. So for all these lookup tables, they're not. You program, the compiler will convert all these logic values to 1 and 0s and store them in the SRAM. Okay, so the lookup table can be converted into anything, any logic gates. It just tells it to be something. Okay, so that's how FPGA cells work, and it has all these interconnection cells and like switches. These are basically transistors. Okay, you turn it on and off to make certain connections. It's a very complicated process being processed by the tools. For us, it's Vivado. For the industry ASIC design, it's usually Cadence or Synopsys. So all these companies are holding like, hundreds of billions of dollars of market value, and you can buy stocks from them if you want. But in the future, all these AI chips from NVIDIA, they do need a lot of digital designers who know how to use Cadence and Synopsys and design all these NVIDIA microchips. Okay, so that is why, for all of us, if you are doing a computer science or just a pure software, which is totally different from hardware. I mean, if you find a job in Google doing algorithm design, you can easily get more than 200K a year, or even more in the future. But for computer hardware engineering, just hardware, for most of the graduated students from our department, and also for students from Colorado mines, I think most of them went to places like the defense sectors and national labs. Usually, like what I said yesterday, it's usually $80 or $90,000 as starting salary, right? But if you go to integrated circuit design industry usually starts with 120K, and very likely you can get like 200K and higher later. Okay, but if you are just doing embedded system design level like microcontrollers and PCB design level, I think there's a cap. So after like 5 or 10 years, I think it's 150K as a maximum almost. Even for national labs, Los Alamos, Sandia, usually as a PI, it's still like 160K. Won't get higher. So if you want to get higher salary in the future, so the IC industry will be the only choice for now, as of now, okay, for the hardware design engineers. 200K or higher, okay? But knowing embedded systems and microcontrollers is also very important to pass the interview, okay, a lot of times. So see, lookup table has all the data already stored in there. And the inputs, it's like a multiplexer, okay? It's an 8-to-1 multiplexer. So depending on the inputs, it selects a certain output. Could you tell the difference between FPGA and microcontroller right now? They're very different, okay? It's the lookup tables or CPUs and memories and all the peripherals. It's very different. So this is our Basys 3 FPGA board. Let's take a look at it really quick. It has this IPGA chip over there. It's probably, I don't know how much, it's somewhere around like $5 to $7. If you buy a lot, the cost of each chip will be definitely lower. Okay, but for microcontroller chips, like this guy, $1, $2 you can buy one. Okay, but so IPGA chips are generally more expensive. Okay, and these chips are cheaper, especially for these 8-bit microcontrollers. There's another company called NXP. I've heard about that. So Soundtracks, which is a company making all these sound decoders in town. They hired a lot of students from us in the past making PCBs. So they like these NXP microcontrollers a lot because they are like only $1 to $2 you can buy each. So they can reduce the cost a lot. But these ones are also very cheap, like $2. Right? These are $5. Very quick quiz question. Why do we still want to use IPGAs sometimes?
Is it quicker?
Quicker, faster. This is 100 megahertz. Okay. So for this one, how fast is this? 16 megahertz. This is 100 megahertz. Why you can drive this one faster? Shorter length. Yeah, it's a shorter or smaller technology can be used for IPGAs. Okay. But you are wondering, hey, you don't even have a CPU on it. So we cannot do anything. Is that true? No. Can you synthesize a CPU and put it into the IPGA? Yes. It's wonderful. You can just write down, compile your Verilog code. You can write your CPU in Verilog, okay, and compile it and synthesize it, and eventually the tool will convert it into a CPU design and implement it into the IPGA. So you can make IPGA using all these lookup tables. It's one of the labs in this semester. Let's take a look. That's why IPGAs are just wonderful. Look at this. So we do all these sequential combinational logic designs and ports and displays, and eventually we will implement a soft core. So soft core is something you write in Verilog, which is a hardware description language. It's industry standard. And synthesize it using Vivado and implement it to the IPGA chip. So eventually you are able to embed a CPU core into your IPGA, and you can program it using assembly code to drive LEDs and driving PWM DC motors and all these kind of peripherals. So for this lab, it's a 2-week lab, and eventually we have this CPU designed and put into the IPGA, and eventually we are making a little calculator with it. It used to be the final last project or lab for the semester. However, it's not enough. So I'm adding 2 more labs for the semester. One is the ADC design. So the IPGA, this IPGA does have an analog to digital converter in it. So we want to use it. And the last one will be the 6502 SoC. So this is a collaboration between the WDC and FLC. And there was a student whose name is Kelvin, graduated 2 years ago. And right now already a leader in the company making satellites. Who benefits a lot from this IPGA class. Let me see, where's Kelvin? Is it Kelvin? Here. I think that was here. Okay, so you can tell it's a different IPGA, so it's good to play with different IPGA platforms. So for the Xilinx IPGAs, the most popular and standard design environment is Vivado. But for the Ultra, right, Ultra, which is the Intel IPGAs, they use Quarters 2, which is another very popular environment. A lot of companies use Quarters 2. For example, the company in town, which is XLRF, which is a defense contractor, it just hired another intern from us. And so what we are going to do is implement the 6502 CPU into this IPGA, and it's basically SoC design. So we are converting this IPGA into a microcontroller like Arduino's. And we are going to program it using assembly and drive a PWM for the servo motor over here. Okay, and you can see the tutorials are already being compiled by him, and I'm gonna convert this tutorial into another one, can fit into this class schedule. Let me see. So this is the design files from him. Let's see. Oh, these are the 6502 single board computers. This is the CPU and all these ports. So there's a kit available from the internet, and we are able to build a computer on the breadboard. It's crazy, so many wires. Imagine build a computer on the breadboard. Breadboard level computer. And the whole thing here was converted into Verilog and being compiled into this IPGA chip. Can you imagine? So this little chip holds the same thing as everything on this breadboard. It's good to see the differences, right? They're doing the same function, the same design. Okay, this is a C. I think it's a C programming environment. So like when you program Arduinos with C language, right? So you're able to program this 6502 chip after you design it, after you implement it into this IPGA. You're able to program using the C language as well. All right, that's the goal. At the end of the semester, we should be able to make an SoC system on chip using IPGA boards. Okay. And let's see. Let's come back to this tutorial. Here's a USB port. You plug in your micro USB here to program it. And this is a USB to serial converter. And here's a HDMI VGA ports for display. We have a lab with VGA. And this is another microcontroller called PIC24. It converts the USB's protocol to something the IPGA can understand. So we have the opportunity to program all different kinds of ports, including USBs. So in your resume in the future for interviews, every single tutorial in this class every week could be something, could be a line in your resume. Okay, for example, you can tell them you know how to so you are familiar with the VGA protocol, and you have done something with the UART, right? So after you finish this tutorial, you have a lot of things to write on the resume. Software, SoC design, USB, SPI, XIDC, yeah. Every week's tutorial is a line in the resume. Okay, a comparison. So Arctic 7 is the name of the IPGA chip over here. It's from Xilinx, which is now AMD. Some features you want to go through. This is a different IPGA board. It's called ZAP board. It's from the same company. It's more powerful. The reason I want to bring this up is because it has a different structure. So whenever we are talking about soft core for our IPGA, the Basys 3 board, it doesn't have any CPU on it, but you can write a Verilog and implement a soft core in it. Okay, but for this ZAP board, it's different. It does have a big area on the chip, allow you to implement your Verilog or soft core, whatever, the same thing as what you can do with the Basys 3 board. However, the difference is it has a hard core in there as well. So it's not just lookup tables. It was designed by the digital design engineers in the company. It's a hard core, and that core is from ARM, which is a British company making most of the CPUs for the modern CPUs of the smartphones, like your Samsung phone, the Snapdragon, all these kind of smartphones are using ARM's CPUs. So the digital design engineers in the industry, just in case, we'll see if we can get students into all these big players. In the future, I hope our graduates can get into places like Qualcomm, Broadcom, Apple, Samsung, all these kind of places, NVIDIA, for example. So they don't design CPUs by themselves. So what's happening is they purchase IP cores, it's intellectual property cores. It's just basically an RTL. It's Verilog. You purchase it from ARM, okay, from ARM, ARM, which is the British company making all the CPUs, and open source, not open source. It's open source for academia. I have the count, but it's not free for the industry. It's very expensive. So I have to purchase all these IP cores and put it into their design and compile the whole design at once, eventually convert it into a integrated circuit design. All right, so this one already has that hardcore in there. It's purchased from ARM. It's called Cortex M something core. It has a hardcore CPU in it, but it can still implement a softcore in the IPGA without any problems. But the benefit is you have a well-designed hardcore. If you want to just directly use that hardcore instead of compiling your own softcore, and you can use that core. It's just a better design. Okay, it's an industry standard design. So sometimes you can consider, when should I use the IPGA? When should I use the microcontroller? I bought a RC boat for our DOT grant, the Department of Transportation grant, which is trying to survey the riverbed by using a sonar mounted to the bottom of the boat. So it's remote control, and eventually we want to just integrate some GPS modules onto the boat, so it's able to drive around the lake and survey the riverbed or lake bed. So we were trying to modify the circuits, and so we opened up the boat and looking at the board. It's just very simple PCB. Has a couple of chips, the memory chips, driver chips, or the CPU or microcontroller chips. So the boat costs about $80, let's say. All right, $80, and it was sold on Amazon. I don't think they can sell millions of units of the boat. Probably, I don't know, 1,000, 2,000 worldwide. It's definitely manufactured in China. Okay, should you hire an NVIDIA engineer to design a ASIC? Let me write it down for you. ASIC. ASIC, which is this guy, with a chip inside. That's a little tiny chip. It's a silicon die. Okay, so manufacture this kind of thing costs about $200,000 for the oldest technology at least. $200,000 just for the design and manufacturing, and you don't even know if that's going to work or not. If it fails, you just have to spend another $200,000 to manufacture, to schedule another manufacturer process for with the company, TSMC, for example. Very expensive, right? So for the 5 nanometer technologies, it costs some places like Samsung, Qualcomm, like a few $1 million, like $5 million, $10 million, just for that prototyping, you know, send it to TSMC for fabrication. It takes like millions of dollars. I mean, the ones we are using is the 180 nanometer technology. For it's good for undergraduates and even for graduate students. I mean, even 180, we're the only place can do this in the state right now. So it's still difficult. Why? Because it's super expensive. So for 180, every time we fabricate a chip, they will give us 25 little dies like these guys, right? 25, the same copy, will give us about 25 copies, so we can test it and try to measure the input and outputs to see if it works. And that's $6,500 just for one design. Can you imagine you have 17 students in the class, if you want to do a tape out. So tape out is another terminology here. Is tape out means send the design out to the foundry for fabrication. It's called tape out. Okay, if I do like 17 tape outs, which means 17 different designs, can we afford it? Yeah, so probably one design for the class, but doesn't make sense. Have to do a lottery. Whose design can be sent to the company for fabrication? It's hard. So it's probably a good idea to do it with the senior son, right? It's just one design. So every single student can contribute $1,000 from the senior son funding from the college, because every one of you have $1,000 for the senior son. So eventually, five people on the team I can collect about $5,000, and I can probably use my faculty activity grant to pay another $1,500. So eventually, we are able to tape out the chip, and this is unique. I mean, it's probably the only one in the state doing this for you guys. But however, for this kind of design, it costs so much money. So, but it's still, this is 25-year-old technology already. It's not even the newest technology we have, but still super expensive. So for the bolts, should the company hire an NVIDIA digital designer to design an ASIC for that little CPU on the bolt and sell it? Doesn't worth it, right? Okay. So for that one, okay, so projector probably costs $2,000, let's say. It has a lot of CPUs in there. Should we hire a NVIDIA level ASIC designer to design the CPU in it, or no? And why? You know, definitely if you want to use a microcontroller like this as a central processing unit, this is probably not good enough. Doesn't have so many pins and ports to control the peripherals. You probably need a more powerful chip. Okay, has maybe 100 pins, can run up to 100 megahertz. Okay, but I cannot sell like 1 million units. The company probably can sell, for example, 2,000 units worldwide. Right, and it's a big box. Doesn't matter if I make it 1 inch smaller, 1 inch bigger. Doesn't matter. Doesn't matter, right? Slightly bigger, slightly smaller. Doesn't really matter. But for the phone, for this guy, doesn't matter. It's 1 inch bigger or 1 inch smaller. Doesn't matter. Yeah. Yes. Okay. So for this guy, you want to use ASICs or FPGAs or microcontrollers. ASICs. So that's why designing ASICs is one of the most highest paying jobs in the industry. Just second to all these pure software or AI engineers in Google or Facebook. Now, who is getting $500,000 a year? We don't care, since we couldn't do it anyway. Yeah, if you can do it, definitely pursue that. But if you cannot, just sit there, do software all day long, you really like doing some hands-on hardware, definitely consider IPGA design, digital verification, hardware design, in IC industry, or ASICs. Okay, there's the places you can potentially get $200,000 in the future. What about that one? I haven't finished that yet. Projectors, the CPUs, or whatever the major processing chip inside. Which one should we use? FPGAs, yes. Just use one of the FPGAs the Zapboard use. Okay, it doesn't matter. Doesn't matter. Like, if I purchase if I do an ASIC, definitely I can make the ASIC super powerful because the ASICs are being used for these Snapdragon chips. Definitely they can be made super powerful, right? But I don't want to spend millions of dollars to hire an NVIDIA engineer to design it. Okay, just hire someone can program FPGAs. Like grab one of the Zapboard FPGAs has ARM cores in it. Okay, even though if I do ASICs, I told you guys, ASICs are expensive. But the thing is, if you sell 1 billion of these CPUs in the smartphones, it's not expensive anymore. You can reduce the cost to just like $10 or something. Okay, it will be really. The cost will be really low. One more question. So for the Snapdragon chips, for example, Snapdragon, I don't know the versions, but the newest version, for example, it won't be just used for this newest Samsung phone, right? There are just so many phone manufacturers on this planet. There are like 5 more in China, and Samsung phones and all these different kinds of phones are using Snapdragon chips. So even though you're only selling maybe 100,000 units for this Samsung A15 phone, but it's okay. There are just so many different phone brands, and they are purchasing the same chip for their phones. It's just same CPUs. So you can basically sell, I don't know, maybe 100 million Snapdragon chips for 2 years. Okay, so it's worth doing that, even though it takes probably $5 million to manufacture that Snapdragon chip with TSMC. Okay, but for that one, it's only sold for $2,000 and 2,000 units every 5 years. What about scientific instruments from NASA, by NASA, or all these Raman instruments, optical instruments? They're only selling like 5 units to MIT, Harvard, Stanford. These are only buyers.
Like the FPGAs.
Probably FPGAs, right? Yeah, you need a faster chip, but you don't really care about the cost. The IPGA chips, eventually you purchase the chip, implement all these RTLs in the chip. It costs like $15 a chip, okay? Who cares? You're only selling 5 units for 5 years. But for these ASICs, a $1 difference will make a huge difference. You are selling like 1 billion units. Make sense?
Yeah.
Okay. But you're wondering, are all these microcontrollers, all of them are that bad? All of them are like 350 nanometer technologies and low performing chips, CPUs. Is that true? Probably not. If you look at all these microcontrollers, they are also microcontrollers, but high performance microcontrollers. This is from ST. This is STM 0. The name is long. I don't want to. It's not necessary to tell that. But the thing is, this could be a little bit faster. I think running up to 50 megahertz, or somewhere between 16 to 50 megahertz. It will be faster than this one, but slower than FPGAs, because it has to accommodate all these slower components in the general purpose CPU. For example, ADCs and other things. Okay, for all these general purpose CPUs, they just have to accommodate all these kind of peripherals in the CPU. It doesn't like all these dedicated digital parts. So a lot of times you can see a company hires an embedded system engineer, but at the microcontroller level, they would prefer some ST microcontroller programming experience. In the past, when I taught microcontrollers, we do have some lectures with ST, but 2 weeks of lectures on ST LEM microcontrollers. But I think in the future probably we should add more, tutorials on it. Okay. Did I answer all the questions on the quiz? Anything else?
I guess the Verilog stuff.
Oh, that's right. Structural is more important. Let's take a 5 minutes break. So let's come back at 55.
Sounds good.
And I'm good on quiz 2.
Yes. Oh, quiz 1.
What's the stall?
The first quiz, Eric, you're Eric, right?
Yeah.
Yeah. The first quiz is the in-class. It's like an in-class exercise.
Okay.
It's open book, open notes. Yeah.
I found it on
Oh, okay. Cool.
this, but
Yeah.
there's a
Hard copy. Yeah.
Yeah.
All right, let's take a look at the Verilog examples over here. So HDL means hardware description language. HDL. Language. VHDL is one of the hardware description languages, and Verilog is another one. And we're using Verilog for this class. You can see a lot of other examples are using VHDL. They're very similar, but using different syntax. If you know how to do Verilog, it's good enough. I think a lot of companies won't exactly just require you to know one of the languages. If you can do either one, I think it's good enough. Okay, to get the job. So Verilog is the one we use. It's very popular in the US. The VHDL is very popular in Europe. So I think doing Verilog is probably more beneficial. And so these are all based on Verilog. So for the first tutorial, you can see there are three different methods to model a digital circuits using Verilog. We'll come back to the Vim stuff later, okay? So look at this one. So there are three different ways to do it. So the first method is called structural modeling. Structural. So for the structural modeling, first you have to name a module. So every single gate, or the whole digital circuit design could be treated as a module. So a basic module as like a circuit block. A lot of times we only care about the input and outputs. It's the module's box, right? Input, output, input, output. So if this type of input is given, what kind of output we should have? It's the design idea behind the scene, okay? So look at this. The module is a box. Keep that in mind. The module is a box. So you have a module and n module to wrap it. So everything should within this the module and n module, just in between. So first you want to claim the ports. Like I said, a box, you care about the inputs and outputs. So for digital circuits, they are just ports. Okay, ports. Input ports, output ports, just ports. Okay? So first you have to claim the ports. It's very simple. If you want to design the box, you need to know what the ports are. So for this digital system, we call it first system, which is the whole thing here, I think. The whole thing is the first system. How many inputs and how many outputs over here? 2 inputs, 2 outputs. Just directly write it down. Don't worry about like which one's the input, which one's the output. Doesn't matter. These are just names. You can name them whatever you want. But I think this one chooses the in and out. That makes more sense. And then after claim it, don't forget this semicolon for the module. And then you start with the properties of the ports. Are they inputs or outputs? Okay? You just have to define this as well. to tell the compiler or the tool, right? So these two ports are inputs and these are outputs. And after that, wires. So wires are not ports. They are internal wires. Wires are just wires. This wire and this wire got two wires in the middle. Just name it wires. This wire and this wire, two wires. Do you have other wires? No, these are all ports. See, this is a wire. No, it's a port. See, it's a port. Right? It's a port. It's connected to the into port. It's a port. It's not a wire. Only two wires. Okay? And for the structural modeling, and or XOR not, these are keywords. Keep in mind, you don't want to name anything as the and. All these keywords. So these are gates. These are functional blocks. So when you put an and here, you can see it's getting bolded. So it's a and. It's a functional block. It's an and gate. It's a keyword. So for AND gate, you instantiate this AND gate, and you name it, give a name to it. I call it gate underscore AND, but you can give a different name. Doesn't matter. Okay? You give a name to it. So what if you have two AND gates? You're gonna start a new line, right? Do another AND, and give the same name or different name. Different name is a different AND gate in the circuit. It has to be a different name, all right? Different name. And then parentheses. First, you have the output. Starts with the output, and then the inputs. Okay? How to deal with the wires for all these instantiations? How to deal with the wires? I just use a wire as a port. It doesn't matter. If the wire is the output, just place that wire's name in front of the parentheses or inside the parentheses, right? So for example, think or out I is a wire. Is that wire? Yeah, or out. Or underscore out is a is a wire. So you can see it's over here. It's the OR gate's output. All right, is it straightforward for the first for the Verilog problem on the quiz? Yeah?
Yeah.
Could you do it?
Maybe. So wires are basically connections that are not directly connected to a port.
That's right. 1, 2, 3 wires. Just name it. Give it different name with all the wires. So these are the ports, and that's the output port. That's structural modeling. Okay. The second, data flow modeling. No difference from the top. Claim the ports, input output, wire, assign. Here's different. Here's different. It's assigning. So assign is a keyword. It's assigning this logic to this wire and assigning this logic to this wire because this is AND logic, this is OR logic, this is XOR logic, this is inverter, it's a NOT. It's inverting this. There's a logic. If it's a 1, it's going to invert it to 0. If it's 0, it's going to be 1 for the output. So you are describing that logic. So if you look at here, definitely these two ORed, getting ORed, and you're getting one output. That is why we have this line here, right? So basically for data flow, you are using assign. All these assign statements instead of gates. And for behavioral, it's using an always statement. Always at something. And something is the sensitivity list. So usually we put the inputs in there, which means when inputs change, we update the logic inside the always block. I'm going to repeat this, all right? So for behavioral modeling, we always use a always at statement followed by a sensitivity list, okay? And we usually keep the input signals into the sensitivity list. So whenever the input changes, we update the logic inside the always block. Why?
I guess because it's like just continuously running, so like.
Continuously running, and if the input doesn't change, do we need to do anything? We don't really care, right? Just the initial state. Okay? So whenever input changes, we update it. It works. It works. Because whenever you don't have an input difference, why do you have to change? Right? That's all the digital circuits, how it behaves. No changes to the input. So something like you design the digital circuits and there's no change to the input. All right? No change to the input. And you are constantly changing the output. Does it make sense? Something's wrong. Nothing changes to the inputs. You're constantly giving different outputs. It's crazy. So that doesn't make sense. It only updates the logic or only updates whatever inside the circuits whenever the input changes, right? That's why we have a behavioral statement, behavioral modeling. So let's take a look at it. So here's the full answer here, okay? First system, no difference. Ports, no difference. And here we have a register type or reg type of variables instead of wire. So in FPGA modeling, a wire you can consider is just a wire. It's called continuous assignment. That makes sense because wires are just continuously assigning. It's like running electrons through the wire. It's not getting controlled. Okay, if here changes, here will change as well. Cannot control it. It's continuously assigning to it. Even for all these gates, for the gates, it doesn't have any control mechanism inside. Whenever the input get changed, your output changes. It's continuously assigning to it. That's why we use a wire. But for register, it's able to store something into it. And it's usually controlled by the clock. So for register type, you can imagine, even though sometimes it's a little bit different, but you can definitely treat it as a D flip-flop. It's a D flip-flop. So whenever clock arrives, when a clock arrives, it assigns the input to the output. That's why it's called a register. It's a register. So it registers the input to the output because the clock arrives. So it's getting controlled by the clock. So sometimes we use for the combinational logic, it's just static gates. We don't have any clocks. So we use the input as a trigger. When input changes, we update the output. But for sequential logic, which is controlled by the clock, we always use something else for in the sensitivity list. And what is that thing, you think? So what should we use? What should we use for the sensitivity signal or list for sequential logic or clocked circuits? So when should we update the circuits for sequential logic? For all these CPUs, all these are super complicated digital circuits, sequential logic, all these kind of things with flip-flops. So when should we update
Conditions change.
the output? Yeah, what kind of condition? Well, I mean, yes, conditions should change. But another thing is, when should we update periodically?
Just like maybe not once every clock cycle.
Yeah, when clock arrives. That's how that works. When clock arrives, we update everything. So in sequential logic, we should use the clock signal as a sensitivity signal. So we always put the clock into the sensitivity list. So you can see later in the semester, for most of the labs, it's going to be, you don't even need to think about it. So what should I put into the sensitivity list? It's almost 100% time, it's just a clock. So starts with always at clock. That's it. Don't even think about it. All right. For this thing, we don't have a clock because it's a combinational logic, right? It's just static gates. Combinational logic, static gates. No sequential, no clock. So just have to put something in the sensitivity list. Otherwise, nothing is going to update. This is this type of statement. You just have to put something into the sensitivity list. So whenever things change, in one of the signals on the list, you update all the signals over here. So what's happening is whenever changes of these two signals are detected, okay, it runs these two lines and update outputs. Make sense? So there is an issue. So what if the inputs are not changing? Combinational logic. It's very possible. If we just directly connect, we're just assigning static logic levels to these two inputs, and we just need one specific logic outputs, and we're not really updating them. They're not changing. One of them is connected to ground. One of them is connected to 5 volts. We're not changing them. So there will be an issue, right? So we do need some initial values for the output. Yeah, it's gonna run this for the first time. It's gonna run it and assign it to the outputs. But at the very beginning, before these signals change, we should give the outputs 2 initial values. But the thing is, you cannot give an initial value to the wire. Think about it. Why? What is a wire? A wire is a wire. It's a wire. Can the wire store a value? No. How can a wire store a value? You can either put it up to VCC or put it down to ground. But that doesn't make sense. Digital signals have to change. Right? If it's either put up to VCC or put down to ground, why do we have to use it? It's not making any sense here. It's not serving the purpose of the digital circuit design, right? So if you wanna change the signal at the signal lines and store some values, they have to be registers. So that's why you need a D flip-flop over here. So it's running a clock, or any kind of signal triggering that clock, triggering that little clock input over here. It just has to be connected to something. Okay, here's the Q output. So they have to be a reg type, register type. To store initial value. Let me see. Let me ask you. Can I store a 0 here? So we are going to cover the structure of the D flip-flop later in the VLSI class. But these structures, they are D flip-flops, they are a latch. They are latches. A latch means it's able to lock a value as the output. It's able to store a value over there. It's going to be stable. It's able to latch it as the output. So it's able to store a value as the output. So for behavioral design, for this example, if we want some initial values for the output, we need a register type of variables for the output. So in this block, we are able to give digital values to these variables because they are register type variables. And keep in mind, this block will only be executed for once. So whenever it starts, assigns the initial values, then this is done. It won't come back and redo this because it's always giving 0 to the output. It's disabling everything in the circuits. Only being executed once, give an initial value, then keeps moving to this digital circuits. It's detecting the input signal changes and then doing something defined by the user over here. That's behavioral. Okay, we'll cover non-blocking and blocking next time on Thursday. So for now, I'm going to run through some of the Vim examples, and so you can expect what is going to be covered in the quiz on Tuesday lab next week. Keep in mind, quiz, closed book, closed notes quiz on Vim. All right? You just have to use it. Just have to know how to use Vim. A lot of people think this is unnecessary, but if you get into industry, the first day is going to ask you to use a VI editor. All right? Take a look at it. So the instructions can be found here. I have a lot of Vim examples. And the lab here as well. Vim installation, preparation is for the lab today. So later this afternoon at 2:30, I think that's the beginning of the lab. And we'll see you in 760. Bring your own laptop, install Vivado into it, since we only have 8 lab desktops over there. And for Vim,
Actually, should we download Vivado before we come?
yeah, I think that would be helpful. Yeah. So for now, you don't have to use command line, but in the future, it's going to be a Linux environment. Just for example, if I start everything from a command line, and oh, there's a way to make this bigger, I think. Properties, font size, layout, terminal. I think just font size. This works. Still didn't help that much. Where is it? Did I close it? Font size 72. Okay, it's better. Let me see. Where should I put it in? How many of you have used Linux command lines? 2, 3. Okay. So in Windows command line is a little bit different, but similar concepts. So if I want to go to a directory, it's going to be CD, right? CD directory. Let's say C. I think I put it in user. So since I know there's a users directory, so I just need to type U and then tab, right? Tab, so directly show users. And then since I know my user's name is YLI, so I just need to type Y and tab. It's going to directly show YLI. It's very similar operation in Linux. So I want to put it into a directory I know, which is Verilog. So I just type V and tab. You can see there are different V's, and apparently it's not under YLI. So it's under documents, I think. So I press D and tab. It directly shows documents, right? And then this, I think I have a Verilog folder over there, and then directly press enter. And didn't get into it. Why? Interesting. Why is that? Do I need to run as a administrator?
But that might be.
Yeah. So CD, C drive. Oh, can I directly bring it up? Oh, it's not here. CD, C drive, users, YLI, documents, Verilog. All right. So if you follow all the steps in the tutorial of the lab, you should be able to have a gvim in your command line. So I directly use gvim, and I will start a new Verilog file, which is, I'll just call it test.v. So Verilog file in Windows is .v. Keep in mind. .v files, Verilog files. Okay, and this is tiny window, and I can use a GUI to change it, but I think there's another way to do that. Let me see if I can still remember. GUI set GUI font size. Is that correct? No. Set GUI font, I think. Okay, I'm gonna make it bigger. Hopefully it's big enough. All right, so you can set for example, during the quiz on Tuesday next week, I'm gonna ask you to, for example, add line numbers to this. It's gonna be set number. You can see a little 1 shows up. Let me make this bigger. Set GUI font equals, let me pick up a bigger one. 36. All right, it's better. So press escape, it's gonna escape. So you cannot edit anything. But you want to insert something, press I, which is insert. You can see insert shows up at the bottom. Insert. So you can type, for example, module. I hate this font. Module. Out 1, out 2, in 1, in 2, right? Things like this. Semicolon. Okay. Input is in 1, in 2. Semicolon. Outputs are out 1, out 2, semicolon, right? Okay. And if you're using, for example, we're using which one? I'm just look at this circuit just in case. Give you an example. Just telling you the answer over here. You can compare it with my answer here. So just look at the circuit on your quiz. So what should we do? We should change it, right? I'm gonna show you. So now it's still under the insert mode. Look at the bottom left. See the insert mode. How should I get rid of it? Escape, right? Escape. Okay, so now I can move the cursor using my keyboard. So the goal is to not using the mouse. You're wondering why? It's just better. So everything, put your finger, 10 fingers on your keyboard, so you can do all this editing. So no mouse, okay? So look at this, it's moving by pressing K. But the thing is, if you're under the insert mode, you press K, see, it's gonna give you a K here, right? Escape it, and K is gonna move the cursor up and down. So down will be J, K will be up, and L will be right, H will be left. Okay? Yeah, GVIM is not an industry standard, and GVIM, a lot of people don't even use it, and people can use a plugin or extension for VS Code. Definitely, yeah, but eventually the commands are the same. You can use the Vim commands in GVIM, in VS Code, in any other editors. But however, eventually, whenever you are collaborating with other engineers in the industry, no matter where you go, eventually it's going to be a Linux environment working on the server, and eventually it's going to be via editors. So just have to know it. How do we move the cursor to the bottom of the code? GG. No. So it's capital G, right? Shift G. And to the top will be GG, lowercase GG. Okay? Capital G, Shift G will move the cursor to the bottom, and GG will be to the top. And insert before that cursor will be I. See? And escape. Insert after the cursor will be A, lowercase a. All right, and insert at the end of the line. For example, line number 1. I want to insert another semicolon after the first semicolon. It's going to be uppercase A, Shift A. Directly get into the insert mode. You can directly start typing. See? Okay. Insert in front of the line will be uppercase A, Shift A. Oh, Shift I. Sorry, Shift I. Will be inserting at the very beginning of the line. Skipping paragraphs will be the $sign, I think. Oh no. Yeah, move the cursor to the end of the line will be $sign, but not inserting, right? And you can skip or move the cursor down and skipping the lines, but just going directly getting to the next paragraph. For example, I can do this, I think. Let me see. So I'm going to create multiple paragraphs just by using the keyboard. It's going to be Shift V. It's visual line. We'll select that line and use J to select the multiple lines and press Y. Yank. What does that mean? But just copy. And then move the cursor to the bottom. Okay, press P. It's going to copy that paragraph. And you can make multiple copies. You can do lowercase o will be inserting after that line, but you don't want to, and press enter and then press P. So it's going to be pasting different paragraphs at the bottom. And you can comment out multiple lines by selecting them first and do a semicolon at the colon and type a command. It's called norm insert this. Okay, so they are being commented out. All right, and you want to delete this, you want to uncomment it, do the same, norm x will delete one column, 2x will delete 2 columns, so you get all these things uncommented. You want to delete the whole line, dd, undo it, u, redo it, shift r. Wait, no, redo it, r, no. Oh, I failed the quiz. Okay, undo it, u, lowercase u, and v, select, d, delete. I think that's the end of the lecture. So we will, I'm gonna meet you here during the lab today, okay? We'll go through more Vim commands briefly, okay? We'll see you later today.
Yeah, see you later.